Imagine a world drowning in carbon, where solutions feel distant and complex. Carbon capture promises to pull greenhouse gases directly from our atmosphere efficiently. But does it really work, or is it just a greenwashed fantasy? Scientists and engineers are racing to make carbon capture scalable and effective. The idea sounds simple: trap carbon before it reaches our planet's atmosphere. Yet the reality is layered with technological, economic, and environmental challenges. Captured carbon must either be stored underground or reused for industrial purposes. Some claim this method can prevent climate disaster within the next decades. Others warn relying on carbon capture may delay crucial emissions reductions worldwide. Today, we explore what carbon capture truly is and how it functions. Industrial plants emit massive amounts of CO2, creating an urgent climate problem. Carbon capture technologies can intercept CO2 before it leaves smokestacks entirely. Once trapped, carbon can be stored safely deep beneath the Earth's surface. Alternatively, innovative companies convert captured carbon into fuels or building materials. Governments are investing billions, hoping carbon capture can meet climate goals. But skeptics question the cost-effectiveness and long-term reliability of these systems. Capturing 1 ton of CO2 can cost hundreds of dollars per year. Despite high costs, some experts believe the technology is essential for survival. Direct air capture machines pull carbon straight from the open atmosphere. These machines require significant energy, which can paradoxically increase emissions otherwise. Researchers are working on solutions using renewable energy to power these systems. Carbon capture is not a single technology, but a variety of methods combined. Post-combustion capture removes CO2 from flue gases after fossil fuel use. Pre-combustion capture extracts carbon before fuels are fully burned or processed. Oxy-fuel combustion burns fuel in pure oxygen, simplifying carbon separation significantly. Storage involves pumping captured CO2 into geological formations deep underground securely. Some of these storage sites are depleted oil and gas reservoirs, proven durable. Enhanced oil recovery uses CO2 injection to extract remaining oil efficiently. Critics argue this process may encourage continued fossil fuel extraction instead of reduction. Monitoring stored carbon is crucial to prevent leaks that could harm the environment. International regulations guide safe storage practices, but enforcement remains inconsistent globally. Carbon capture can also integrate with bioenergy, forming BECCS systems for climate mitigation. BECCS stands for Bioenergy with Carbon Capture and Storage, a controversial strategy. It uses plants to absorb carbon naturally, then captures emissions when burned for energy. Proponents claim BECCS could remove gigatons of CO2 annually if scaled properly. Opponents worry about land use conflicts, threatening food security and ecosystems severely. Economic feasibility often limits large-scale deployment, making governments cautious investors. However, innovative startups are developing smaller, modular systems to reduce costs. Public perception is critical. Many fear carbon capture delays renewable energy adoption. Misunderstanding can lead to opposition, reducing funding and slowing technological progress. Transparency about risks and benefits is essential for societal trust and support. Carbon capture also opens opportunities for creating new materials, like carbon-negative concrete. Such innovations can permanently lock carbon into everyday products, reducing emissions indirectly. Yet scaling these innovations requires collaboration between industries, governments, and researchers. Success stories exist. Iceland's Climeworks facility captures thousands of tons of CO2 yearly. Still, this is a fraction of global emissions, emphasizing the scale challenge ahead. Critics warn carbon capture is not a silver bullet, but a complementary solution. Real climate progress demands reducing emissions while deploying carbon removal strategically. Policy incentives, carbon pricing, and regulation are driving the industry's growth cautiously. Private sector investment is increasing as companies face emissions disclosure and pressure. Carbon markets offer financial motivation for companies to capture or offset emissions. However, carbon accounting must be rigorous to avoid false environmental claims entirely. Scientists emphasize transparency, accuracy, and verification to make carbon capture credible. The technology continues evolving rapidly, with breakthroughs in membranes, solvents, and sorbents. New materials aim to capture carbon more efficiently while using less energy. Engineers are exploring mineralization, turning CO2 into rock for permanent storage safely. Each method carries trade-offs between cost, efficiency, and environmental impact realistically. Carbon capture is increasingly seen as Carbon capture begins with separating CO2 from other gases and industrial emissions. Post-combustion methods typically use chemical solvents to absorb carbon dioxide efficiently. Amines are common solvents that bond with CO2 before releasing it for storage. Pre-combustion capture converts fossil fuels into a mixture of hydrogen and CO2. Hydrogen can then be used as clean fuel while carbon is stored safely. Oxy-fuel combustion burns fuel in pure oxygen, creating a CO2-rich exhaust. This simplifies carbon separation but requires specialized, costly equipment for operation. Direct air capture removes CO2 from the open atmosphere using large fans. These systems require massive energy inputs, often sourced from renewable power. Captured CO2 is compressed into a liquid form for transportation and storage. Pipelines are often built to transport CO2 to storage locations underground securely. Geological formations like depleted oil reservoirs or saline aquifers are ideal storage sites. Monitoring these storage sites ensures the carbon remains trapped over decades effectively. Any leakage could undermine environmental benefits, making regulation and oversight essential. Enhanced oil recovery injects CO2 into oil fields, helping extract remaining oil efficiently. Critics argue this perpetuates fossil fuel use, potentially offsetting capture benefits significantly. Carbon utilization transforms CO2 into fuels, chemicals, or construction materials creatively. Carbon-negative concrete can store CO2 permanently, reducing emissions from building projects. Other methods convert CO2 into synthetic fuels that can replace fossil-based energy. Scaling these technologies requires collaboration between researchers, industries, and governments worldwide. Cost remains a major challenge, with high energy demand limiting widespread adoption. Capturing 1 ton of CO2 can cost hundreds of dollars using current technology. Reducing costs involves new materials, better solvents, and energy-efficient system designs. Membranes and solid sorbents are being tested as alternatives to chemical solvents. Mineralization uses natural reactions to turn CO2 into solid carbonate rocks permanently. This method promises long-term storage with minimal risk of leakage or reversal. Bioenergy with carbon capture and storage combines plant growth with emission removal. BECCS can theoretically remove CO2 from the atmosphere while producing renewable energy. However, BECCS may require vast amounts of land, impacting food production severely. Environmentalists stress that carbon capture cannot replace immediate reductions in emissions. It should complement renewable energy, energy efficiency, and sustainable infrastructure development. Governments worldwide are introducing incentives, subsidies, and carbon pricing to support adoption. Private companies are investing heavily, seeing potential profit in carbon reduction credits. Verification of captured carbon is critical to avoid greenwashing and ensure credibility. Scientists emphasize rigorous accounting, monitoring, and transparency in carbon capture projects. Some countries, like Iceland, have successful pilot plants demonstrating real-world feasibility. Climeworks captures thousands of tons of CO2 annually, showcasing technological potential effectively. Yet, global emissions still exceed capture capacity by a wide margin currently. Public opinion varies. Some see carbon capture as hope, others as risky distraction. Misunderstanding the technology can lead to skepticism or political resistance frequently. Awareness campaigns aim to educate citizens about realistic expectations and climate benefits. Ethical considerations also arise, particularly regarding land use and energy sourcing. Renewable-powered capture systems aim to minimize additional emissions from energy consumption. Partnerships between governments, universities, and industries accelerate innovation and deployment significantly. Research continues on advanced solvents, sorbents, and low-energy capture methods globally. Policy frameworks help regulate storage, transportation, and monitoring, ensuring safety and compliance. International collaboration is essential to standardize best practices and share lessons learned. Financial models, including carbon credits, incentivize companies to invest in capture technologies. Carbon capture could become a major industry, creating jobs in engineering and maintenance. Public-private partnerships often fund demonstration projects, reducing risk for private investors. Challenges remain, including energy costs, equipment durability, and long-term storage reliability. Breakthroughs in AI and automation may optimize carbon capture efficiency and monitoring efforts. Some startups focus on modular systems that can be deployed locally and scaled rapidly. These smaller systems reduce upfront costs, making carbon capture accessible to more regions. Innovations in CO2 utilization turn waste carbon into valuable mat. Several countries have implemented carbon capture projects to combat rising CO2 emissions. Iceland's Climeworks facility captures thousands of tons of CO2 annually from air. This captured carbon is injected underground, where it mineralizes safely into rock. Norway's Sleipner project has successfully stored CO2 in saline aquifers since 1996. The project captures about 1 million tons of CO2 each year efficiently. Petronova in Texas captured CO2 from a coal-fired power plant successfully. Captured carbon was used for enhanced oil recovery, extending existing oil production. However, the project faced high operational costs and eventually shut down temporarily. These examples show both potential and limitations of current carbon capture efforts. Direct air capture plants exist, but their scale remains small compared to emissions. Industrial applications like cement and steel production are increasingly exploring capture technologies. Cement production alone accounts for roughly 8% of global CO2 emissions currently. Capturing carbon from such industries is technically feasible, but expensive and energy-intensive. Startups are experimenting with modular, smaller-scale systems to improve accessibility and cost-effectiveness. Companies like Carbon Clean and Climeworks focus on innovations to reduce energy consumption. Some plants integrate capture with renewable energy, lowering the overall carbon footprint. Pilot projects demonstrate feasibility, but scaling remains the biggest challenge for adoption. Energy requirements for direct air capture can offset some of the captured carbon. Using solar or wind energy helps mitigate this paradox effectively. Carbon capture and storage combined with bioenergy is still experimental. BECCS can theoretically remove CO2 while producing energy, but land use is concerning. Large-scale BECCS may compete with agriculture, threatening food security in vulnerable regions. Despite challenges, governments continue funding pilot and demonstration projects worldwide. The U.S. Department of Energy invests heavily in carbon capture research initiatives. European nations also support capture projects through subsidies and carbon pricing programs. China has several industrial CCS projects under construction to reduce coal emissions. Public-private partnerships are key to funding and operating these high-cost technologies efficiently. Costs remain a major hurdle, making carbon capture dependent on financial incentives significantly. Carbon credits offer companies motivation to invest in carbon removal technologies responsibly. Verification of captured carbon is essential to ensure environmental claims are accurate and credible. Misreporting or greenwashing risks damaging public trust in carbon capture technology permanently. Monitoring stored CO2 ensures it remains trapped and does not leak back into the atmosphere. Sensors, satellites, and underground monitoring systems are commonly used for verification today. Leakage events, while rare, could undermine decades of captured carbon's environmental benefits. Enhanced oil recovery using captured carbon remains controversial for its potential environmental trade-offs. Some experts argue this prolongs fossil fuel dependence instead of reducing emissions effectively. Others claim it provides economic incentives that support carbon capture investment expansion. Real-world examples highlight the delicate balance between technology deployment and environmental responsibility. Storage methods vary, including saline aquifers, depleted oil fields, and mineralization approaches. Mineralization permanently converts CO2 into solid rock, reducing long-term environmental risks substantially. Economic feasibility influences which storage method is chosen for a specific project location. Policymakers must weigh costs, benefits, and environmental impacts before approving projects carefully. Some projects have struggled due to high costs and insufficient political or financial support. Public perception can make or break a carbon capture initiative depending on transparency. Communities need to understand benefits, risks, and local impacts for effective acceptance. Transparency in reporting and education campaigns improve public trust in carbon capture efforts. Lessons from past failures guide future projects towards safer, more efficient implementations. Partnerships between governments, universities, and private companies accelerate learning and innovation collaboratively. Breakthroughs in solvents, sorbents, and membranes continue to improve efficiency and reduce costs. Technology is evolving rapidly, but deployment speed must match urgent climate mitigation needs. Real-world projects show potential, but scaling is the biggest challenge yet globally. Economic incentives, regulations, and innovation must align for carbon capture to succeed widely. Pilot and demonstration projects act as learning hubs for broader, global deployment strategies. Carbon capture technology remains expensive, but costs are gradually decreasing with innovation. Governments provide subsidies and tax credits to encourage adoption of these systems. In the United States, the 45Q tax credit rewards verified carbon sequestration efforts. Europe offers similar incentives under the EU emissions trading system for CCS projects. High upfront costs make private investment risky without financial support from governments. Public-private partnerships help share costs and reduce financial risks for new projects. Carbon pricing creates a financial incentive for companies to capture or offset emissions. Markets for carbon credits allow firms to trade captured CO2 for economic benefit. Verification and certification are essential to prevent greenwashing in carbon credit markets. Transparent monitoring ensures that claimed reductions match actual carbon captured reliably. Some economists argue that carbon capture may only be viable with high carbon prices. Companies are exploring cost-effective modular systems for industrial and local-scale deployment. Research and development investments drive technological improvements, reducing energy consumption drastically. Innovation in solvents, sorbents, and membranes increases capture efficiency while lowering costs. Future systems may integrate renewable energy, minimizing the carbon footprint of operations. Governments also fund pilot projects to demonstrate feasibility and inform policy decisions. Policies can encourage industries like cement, steel, and power to adopt CCS. Carbon capture aligns with climate targets, complementing renewable energy and emissions reduction strategies. Investment in infrastructure for CO2 transport and storage is crucial for scaling solutions. Pipelines and storage facilities require careful planning and long-term regulatory oversight effectively. Economic feasibility varies by region, depending on energy costs and industrial emissions density. Storage site accessibility influences project viability and long-term carbon sequestration potential significantly. Some private companies develop business models using captured CO2 to create commercial products. Carbon utilization can produce synthetic fuels, plastics, or carbon-negative construction materials efficiently. Turning captured CO2 into valuable materials creates circular economy opportunities while reducing emissions. International cooperation is essential to standardize regulations, monitoring, and best practices globally. Cross-border projects may share knowledge, technology, and financing for greater impact worldwide. The International Energy Agency tracks CCS deployment, highlighting trends and potential improvements clearly. Experts predict carbon capture may remove billions of tons of CO2 by mid-century. This would significantly support achieving Paris Agreement targets alongside emissions reductions. Scaling up requires careful coordination of technology, finance, policy, and public engagement. Regulatory frameworks ensure safe storage, monitor leakage risks, and promote environmental integrity reliably. Public acceptance is critical, requiring transparency about risks, costs, and societal benefits. Education campaigns inform citizens about CCS's role in complementing renewable energy strategies. Carbon capture may enable continued use of certain industrial processes while reducing emissions. Critics warn reliance on capture could delay essential transitions to clean energy systems. Combining CCS with renewables ensures mitigation without perpetuating fossil fuel dependence unnecessarily. Technological breakthroughs, including AI optimization, promise efficiency gains in monitoring and operations. Future carbon capture systems may be smaller, modular, and adaptable to multiple locations. Innovation in direct air capture could allow CO2 removal from the atmosphere globally. Integration with bioenergy and negative emission strategies could enhance climate mitigation potential. Investors consider environmental, social, and governance factors when funding carbon capture projects. Risk management strategies mitigate financial, operational, and environmental uncertainties in CCS projects. Successful implementation can create jobs, stimulate innovation, and drive regional economic growth. Policymakers must balance environmental goals with economic feasibility and industrial competitiveness carefully. International standards help ensure captured carbon is measured and reported consistently and transparently. Collaboration between researchers, industry, and governments accelerates learning and reduces duplication globally. Market mechanisms can reward companies that successfully deploy capture and storage technologies. Carbon capture is increasingly seen as an essential tool in net zero strategies worldwide. Future projections indicate CCS will complement renewable energy, energy efficiency, and reforestation efforts. Carbon capture technology represents a hopeful tool in the global climate mitigation effort. Its potential lies in reducing emissions. While society transitions to cleaner energy sources, scientists emphasize that it works best when combined with renewable energy development simultaneously. Direct air capture remains expensive, but demonstrates possibilities for large-scale carbon removal solutions. Geological storage provides long-term carbon retention, monitored closely to ensure environmental safety. Carbon utilization transforms captured CO2 into products like fuels, chemicals, or construction materials. Emerging technologies continue improving capture efficiency and lowering operational costs consistently. International cooperation accelerates research, sharing knowledge and resources across borders effectively. Policy incentives, such as grants or tax credits, encourage investment in carbon capture projects. Public awareness is crucial, fostering informed discussions about carbon capture's advantages and limitations. Education campaigns help communities understand potential risks and benefits clearly. Companies deploying carbon capture must maintain transparency and follow strict environmental standards. Independent audits verify that claimed emission reductions are accurate and accountable reliably. Carbon capture alone cannot solve climate change. Reducing fossil fuel use remains essential. Experts recommend integrating multiple strategies: renewables, energy efficiency, and behavioral changes collectively. Innovations in materials, such as advanced sorbents, improve carbon capture performance steadily. Some captured carbon is used to create durable construction materials, reducing overall emissions. Synthetic fuels from captured CO2 offer environmentally friendly alternatives to conventional petroleum products. Carbon capture projects must consider local ecological impacts and avoid unintended consequences responsibly. Collaboration between governments, private sectors, and research institutions drives technology advancement efficiently. Carbon markets provide financial incentives, encouraging industries to invest in emission reduction solutions. Regulations and standards ensure projects operate safely, minimizing environmental or social risks effectively. Case studies show carbon capture can remove hundreds of thousands of tons of CO2 annually. Yet widespread adoption requires further cost reductions and supportive policy frameworks consistently. Carbon capture represents one piece of a larger climate action puzzle worldwide. While promising, it is not a replacement for transitioning toward clean, renewable energy sources. Communities near storage sites benefit from strict monitoring to prevent leakage or contamination hazards. Scientists use simulations and modeling to predict long-term storage stability accurately. Funding from governments and private sectors supports pilot projects demonstrating feasibility effectively. Innovation continues in direct air capture, aiming to remove CO2 efficiently from ambient air. Public trust grows when projects adhere to transparency, safety, and environmental responsibility standards. International agreements encourage knowledge sharing and technology transfer between countries collaboratively. Carbon capture can complement nature-based solutions such as reforestation and soil carbon management. Combining multiple strategies strengthens global climate mitigation efforts holistically. Education about carbon capture promotes understanding of technological possibilities and realistic expectations responsibly. Policy frameworks should balance innovation incentives with rigorous environmental safeguards fairly. Continuous monitoring ensures carbon does not escape from storage, maintaining long-term effectiveness reliably. Governments play a key role in funding and regulating carbon capture initiatives responsibly. Industry adoption depends on cost effectiveness, technological reliability, and regulatory compliance consistently. Public engagement encourages accountability and fosters support for sustainable climate solutions effectively. Scientists explore alternative storage sites, including depleted oil fields and saline aquifers, safely. Carbon capture technology has evolved significantly, yet research is still crucial for improvement. Transparent reporting helps the public and regulators assess the true environmental benefits accurately. Combining carbon capture with renewable energy maximizes emission reduction potential globally. Utilization of captured CO2 creates economic opportunities while addressing environmental challenges simultaneously. Large-scale deployment requires collaboration among engineers, policymakers, and environmental scientists consistently. Pilot projects provide valuable data for scaling up carbon capture efficiently and safely. Some companies successfully integrate captured carbon into concrete, reducing life cycle emissions significantly.